Now I'm recording. Okay, there we go. So we have an exponential equation because we have variables in the exponent, and we have a 1/4 and a square root of 2 as our base. Do we need to use logs here? No, because both bases can be written as a power of what? 2. You have to recognize that. So let's go ahead and just write parentheses to the x minus 1, parentheses to the x plus 1, and 1/4 is 2 to the what power? Negative second. And the square root of 2 is 2 to the what? 1/2 power. Okay, now when we raise the power to a power, we multiply. So we distribute the negative 2, we get negative 2x plus 2, and we distribute the 1/2, and we get 2 to the 1/2 x plus a half. So, right? So, did you remember your word so or therefore? So, negative 2x plus 2 must equal 1/2 x plus a half. Now, yesterday, we eradicated the fractions in here. Second period embraced the fractions, and we got the same answer. Um, it turned out that it was a little bit easier to eradicate the fractions in hindsight. So I'm going to go ahead and do that. I'm going to multiply both sides by what?
1/2.
No, not 1/2. I want to get rid of the 1/2. By 2. That's the LCM of your miniature denominators. Okay, new column. Yum. So I get negative 4x plus 4 equals, when I distribute, I get x plus 1. Your fractions will show back up in your final answer, but if you don't like them at this point, multiply both sides by the LCM of your denominators. Okay, now I bring this across and I get negative 3x equals negative 4 minus 1, or plus 1 is negative 3, and now I divide both sides by negative 3, and I get what? 1. I don't think that's right either. Did I do something wrong? Negative 4x plus 4. Oh, yeah. Yeah, avocados from Mexico. Mr. Corby's not starting this game. Yeah, when you bring it, see, that's what happens when you're hasty and you make wasty, right? This x comes across and becomes negative x, so that's supposed to be negative 5x, and then you bring the 4 across and it becomes negative 4 plus 1, so that's right. And then we divide through and we get 3/5. 3/5, and that's the final answer. Yeah, I got 1, and I was quickly plugging it back into the original problem, and I was quickly realizing that it didn't work because 1 does not equal 2. If you plug the 1 into the original problem, you get 1 equals 2, and we know that's not right. Yeah. Now 2 could equal 1, right, in a very happy marriage, but 1 can't equal 2. Well, I guess if 2 equals 1, then 1 has to equal 2. Whatever. The answer is 3/5. Yeah. Any questions on that? Learn from me. If you're trying to do Wordle while you're trying to do math, your brain is competing with two different things. So solve that Wordle in 2 steps and get on with the math. Yeah. All right. Let's move on to example C. We are going to do the next. Yeah, I don't know if that works. I should have thought that out a little more. All right. So is this an exponential equation? Yeah, we got exponents with variables. I got a 3 in front of my base on the left and a 4 in front of my base on the right. Is there any way to like divide both sides by 3 or divide both sides by 4 to simplify that or get rid of it? No. If I divide the left by 3, then I'm going to get a 4/3 on the right-hand side, which means I have a fraction, 4/3, yucky, yucky, gross, gross. If I divide both sides by 4, I'm going to get a 3/4 on the left. I don't want a fraction at all. So I'm just going to leave it as this. Now, can I write the bases 5 and 6 simply as a power of each other or a third party common base?
Yeah.
What?
Ln.
No, we're not using ln. Remember I said simply,
Oh.
right? We do know, again, based upon what you said yesterday, 5 to the x is the same as e to the natural log of 5 to the x, right? But I don't want to go that route. I don't want to set the bases the same like that. So because I can't write 5 as the power of 6, and I can't write 6 as the power of 5, and I can't write both of them as a power of a third party base easily, okay, who comes to the rescue? LN. Oh, yeah. Oh, okay. I thought you were referring to this, Brady, what we did yesterday. No. So LN. So we're going to take the LN of both sides. So I'm going to get the natural log of 3 times 5 to the 2x minus 1 equals the natural log of 4 times 6 to the 1 plus x. Okay? Take the natural log of both sides. Now we're going to use properties 1, 2, and 3, whatever they are, to expand this out completely, and we're going to do it in one fell swoop. Are you ready? I'm going to get the natural log of 3 plus bringing the 2x minus 1 out front, because it's the exponent, I get the natural log of 5. On the right, I do the same thing. It's the natural log of 4 plus, I'm going to call that x plus 1. 1 plus x just kind of gives me an itch. I'm going to commute the terms. X plus 1. Natural log of 6. Yes, yes? Everyone okay with that? That sits well with y'all? All right, now, remember what we did yesterday over here. In order to get the like terms together on the same side, we have to expand out this line. There's no exception here. We got to do the same thing. I have to distribute the natural log of 5, which is a number, into the parentheses, and I got to distribute the natural log of 6, which is a number, into the parentheses. Okay? So the natural log of 3 is just hanging out, and then this becomes 2x, natural log of 5, minus 1 times the natural 5 is minus natural log of 5.
Where are you putting the natural log of 5? Oh, wait.
I'm just putting it in the back.
Okay.
So 2x times the natural log of 5, I'm just calling 2x ln of 5. And this becomes the natural log of 4 plus x natural log of 6 plus 1 times the natural log of 6 is natural log of 6. Now remember, there's a lot of logs floating around. But if there's no x in your term, and which terms don't have x? The first one, the third one, the first one, and the third one. There's 4 terms that don't have x in them. That means that those terms are just numbers, right? They're just numbers. We can evaluate them on a calculator to 3 decimals if we want. The other terms do have x in them. So we're really back in algebra 1. We just have natural logs floating around. Remember what we did? We collected the x's on the left and our numbers on the right. And that's what we're going to do here. So let's go ahead and collect our x's terms first. So 2x ln of 5 is already on the left, so he just stays put. And then the x ln of 6 has to come across, doesn't he? So that becomes a minus x ln of 6. Okay? And that's all that I'm going to put on the left. On the right-hand side, I'm going to put all my numbers. Well, I already have the natural log of 4 over there, and I already got the natural log of 6 over there. So those two fellas stay. The other two fellas, they come across, and remember you change the term sign when they come across. So that's going to be plus the natural log of 5 and minus the natural log of 3. Now I got 2x terms on the left and just a number on the right. That's the sum or difference of those numbers right there. Okay, it's an exact value. Now, here's where it's a little bit different from Algebra 1. In Algebra 1, you might just have 2x minus x. They're like terms. These are not like terms, but they do both have an x in them. So how are we going to get it down to a single x? Well, what did we do yesterday? We factor out the x. Yeah, so that's the skill right there. We're going to factor out the x, and that leaves us 2 ln of 5 minus ln of 6. And on the right-hand side, if you want to start condensing that, like, can we condense this right here? What's the natural log of 4 plus the natural log of 6? That's just the natural log of what? Nope. Nope. 24. Oh, yeah, I didn't hear you say the 2 in front. It's 24. I thought you said 4. Remember, a sum goes to a product. So we can condense that if we want. Do you want to condense this right here? Do you want to call that natural log of 5/3? Do you want to introduce a fraction?
No.
Yeah, no, I wouldn't. So I'm just going to leave that as the natural log of 5 minus the natural log of 3. Oh, by the way, could we have just, instead of condensing the 4 and the 6, could we have condensed the 6 and the 5 and called it the natural log of 30? Yeah, we could have. Could we have used the natural log of 4 and the natural log of 5 and called it the natural log of 20? Yeah, we could have. There's 3 terms. We can combine them however we want. I just combined the first 2 because they happen to be written side by side. All right, now, the last thing that we do, since we have x times some number, the thing that I just highlighted on the left side is just a number, right? How do I undo multiplying by that number? I divide by that number. So our final answer here is going to be x equals whatever we have on the left. Now, do you want to condense this? Do you want to call that the natural log of 5 times 24? What would it be? What is 5 times 24? Like 120. In fact, I think it is 120. So it's the natural log of 120 minus the natural log of 3. all over 2 natural log of 5 minus the natural log of 6. Now we can play some more, right? There's your final answer. You actually got x equals something. We can play some more now if we want. Do you want to condense the numerator even more to the natural log of 120 divided by 3? I would do that here because 3 is the factor of 120, right? So I'm going to do that off to the side so I don't have to write everything all over again. Here's me on my workbench. This is the numerator, my workbench. That becomes the natural log of 40. I like that. That's a simple looking numerator. So the natural log of 40 over, is there anything we can do in the bottom? I could bring the 2 back up as an exponent of the 5, couldn't I? And that would be the natural log of what? 25 minus the natural log of 6. Do you want to condense the natural log of 25 minus the natural log of 6 to the natural log of 25 over 6? Is that something we want to do? Yeah, nothing divides out, and we get a fraction in the denominator of a fraction. So that's yucky, yucky, gross, gross. YYGG. I wouldn't do that. But this answer, 40 is still a relatively small number, isn't it? So this right here, I think, is a dandy of an answer. Now, if you wanted, I could have left it like this. I could have just left my entire right side like that, and that could be my numerator divided by this entire thing like that. It's possible, right? I could have left it like that. But we learn to play with the logs by condensing if we need to, and we can get it down to something that is relatively manageable. Okay, 120 is kind of getting a little bit too big for my britches. I don't necessarily want to do anything bigger than 120, but it worked here, and especially when we divided it by 3, it divided out. Now, if you wanted to do the divided by 3 first, look up here. You could have done this. You could have done the natural log of 6 minus the natural log of 3. What is the natural log of 6 minus the natural log of 3? That's the natural log of what? 2. That's the natural log of 6 divided by 3. So you could have, there's a lot of different ways you could have combined those terms right there. I just happened to combine the first two. Okay, learn to play with your logs, right? Coochie coochie coo. All right. There's lots of different right final answers. You just have to match it up to a multiple choice question. All right. This one, by the way, this one makes a great quiz question. And I might say on the quiz so that we all get the same right answer, I might say on the quiz, do not simplify your final answer so that we all get the same thing. If I said do not simplify your final answer would be this right here in the box for your numerator, all over this right here in the box for your denominator. Okay? Because there's lots of different ways to condense it. We want the same answer. On a test, if this makes a great quiz question, you know it makes a great test question. As a multiple choice question, this might be the answer choice. And you'd have to kind of mess around with it until you match it up to one of the answer choices. Fun. Okay. Any comments or questions on how we do a problem like this? Take the log of both sides, fully expand, distribute, collect x's on the left, numbers on the right, factor out an x, and then divide through, and you solve for x, and then you play, right? Then you play. Okay. Let's look at some other types of exponential equations that are a little bit more nuanced. For example, example 4a, we have e to the x over e to the x minus 1. Is this an exponential equation? Yeah, we have a variable exponent. We have a variable exponent. How would you solve something like this in algebra 2 if instead of e to the x, it was just x? X over x minus 1. What would you do to solve it in algebra 2? Say what? You would bring this up? How? It's a quantity, right? It's a quantity, so you can't just bring the x up. No, you would. It's kind of like getting rid of the fractions like we did them. You would multiply both sides by the denominator, wouldn't you? Yeah, so that it would divide out. Well, guess what? It's no different here. It's no different here. We're going to take this and we're going to multiply by e to the x minus 1 in parentheses, and we're going to multiply this side by e to the x minus 1 in parentheses. On the left side, if you want to put that over 1, you can. What happens with your e to the x's minus 1s is they divide out. And we're left with e to the x equals, if I distribute here, I get 5 e to the x minus 5. Now I just collect my variables on one side. So if I put my phone away and I bring the 5e to the x over to the left, it becomes, I'm going to do this in two steps because I messed up last time, minus 5e to the x plus, I'm going to call that 1e to the x equals negative 5. Are those like terms? Yeah, but I haven't combined them yet because I messed up last time. I'm doing it in two steps. Those are like terms, right? They're both e to the x terms. So what's minus 5 plus 1? You said it. You said it, Brady. It's negative 4 e to the x equals negative 5. Now I want to solve for e to the x. So I divide through by negative 4. Remember, we're peeling back the layers to get at the x. Negative 4 is in the way. Negative 5 divided by negative 4 is 5/4. Now I've turned it in to an equation like we've been solving up above. Can I get the bases the same here? Can I write 5/4 as the power of e very easily? No. So who comes to the rescue? Natural log. Now, watch this. You don't have to show this step. The natural log of e to the x equals the natural log of 5/4. You can skip this step if you want. And you can go straight to this. What is the natural log of e to the x? It's just x because the natural log of e is 1. Yeah. So you get x equals the natural log of 5/4. No, because we didn't use the theorem here. We just took the natural log of both sides and we evaluated it. The natural log of e to the x is x. That's only when you get the bases the same, right? Now, we got to make sure that it works. Here's one little caveat to this problem. Exponential functions have domains of all real numbers, but I started, and we maybe should have thought about this before we even began. I started with a variable in the denominator. You remember when we spent all that time fighting domains? We can't divide by 0, can we? So we got to make sure right here. Let's just make sure. E to the x minus 1 cannot be 0. E to the x minus 1 cannot be 0. Would you agree? Good. You have to agree. Otherwise, you're going to be wrong. Bring the 1 across and you get e to the x can equal 1. I can take the natural log of both sides now, can't I? The natural log of e to the x is x. Cannot equal the natural log of 1. What is the natural log of 1? 0. So x cannot equal 0. If you get 0 as a solution, you have to toss it out because it makes the denominator 0. Now that's important because notice when I multiplied both sides by e to the x minus 1 to get rid of the denominator, I turned it into an equation that no longer has the denominator. So there's no longer a restriction. Now, you look at your final answer. Is the natural log of 5/4 equal to 0? No. So is it allowed? Is it legal? Yes. Okay. So it's barely legal. All right. That sounds like a risque video that used to be able to buy off the internet. Girls Gone Wild, barely legal. Right? Yeah, I know. You don't do that anymore. They don't sell that stuff anymore because now there's something called internet with privacy browsers. Right, Ryan? I don't know. They used to have commercials for that. Like you'd be watching MTV, like you'd be watching Rob Dyrdek on Ridiculousness, and there's a commercial for Girls Gone Wild, and you're like, those girls should be at home doing their math homework. That would solve a lot of their problems. Okay. You never saw Guys Gone Wild. I guess there weren't a lot of women buying those DVDs. All right, so let's move on to the next one. Letter B. I got 3x e to the x equals x squared e to the x. Ooh, ooh, ooh. I can divide both sides by e to the x, and I get 3 equals x. And I'm done. That does seem too simple. Do you recall what I said earlier in the year when you divide out variables? Don't lose variables from an equation. Because when you lose variables, you lose solutions possibly. So when I divide out the e to the x's are completely gone. Now the x doesn't completely vanish. We're still left with an x on the right hand side. So that wouldn't necessarily be illegal, but the e to the x's are gone. So that's not how we're going to do it. So don't do it that way. Here's what we're going to do instead. We have variables on the left, we have variables on the right. Whenever you have more than one variable term, and we have 2 here, you're going to want to get everything on one side and set it equal to 0. So let's do that. You get 3x e to the x minus x squared e to the x, and it equals 0. Now, once something is equal to 0, your goal is to what it? F it. We want to F it, right? Because then we can use the zero product property that allows us to set each factor equal to 0. The first rule of factoring is to cry, then to panic, then to Google it, and then to look for a GCF. What's the GCF here? X e to the x. It was that very thing that we were anxious to divide out in the very beginning. We still divided it out here, but we didn't lose it. We divided it out and we put it in the front as a factor. Now we're left with 3 minus x equals 0. Now I have three factors, believe it or not. I have an x, an e to the x, and a 3 minus x. The zero product property says I can set each of them equal to 0 and solve. So I've made three equations out of one, which seems like thrice the work. However, the equations are much easier to solve. All right. Is there anything to solve on x equals 0, or is it good? It's good. What about the middle one? E to the x equals 0. I got to solve it by doing what to both sides? Natural log it. So if I take the natural log of the left, I just get x, right? And I get the natural log of the right is the natural log of 0. Can I leave my exact answer like that? What is the natural log of 0? No, not 1. The natural log of 1 is 0. But the natural log of 0 at x equals 0, what do we have on the graph at x equals 0? No. No. It's 1, 0. But what at x equals 0, what do we have on the graph at x equals 0? A vertical asymptote. Thank you, Ryan. So what is the value of the natural log of 0? DNE. Yes, thank you. We finally got there. Don't forget to remember stuff, guys. So that one didn't generate a solution. E to the x can't be 0. Another way to think about it is e to the x can't be 0 because what does e to the x have at 0, at y equals 0? A horizontal asymptote. E to the x will never equal 0 because the natural log of 0 is undefined. Now this one gives us x equals 3. Now we got to be careful. Over here we said, oh, there was a prospect of dividing by 0, so our solution couldn't be the value that gave us 0 down there, which was 0. And it wasn't. Are we at risk? Do we have any domain restrictions here? No, we're not dividing by 0. We're not taking the square root of a negative, and we don't have logs. Now, if you ever have logs in your equations, which we haven't started those really in depth yet, you have to be careful because you can only take the log of a positive number. But e to the x has a domain of all real numbers, and there's no denominator here. So do both of these box solutions work, 0 and 3? Yep. So that's why we don't get rid of variables. We lose variables, we lose solutions. We lost an x. It still appeared, but we lost the 0 by dividing through by the x. Okay, you're going to like the next one. You've liked them all so far, I know. But you're going to like this one also. 3e to the negative x minus e to the positive x equals negative dose. Oh boy. It is an exponential equation. What do you notice about the powers now? They're opposite, right? Do you think I can separate it so that I get the base is the same? E to the x equals e to the negative x. So x equals negative x. Do you think I'm going to be able to do that? I'm not going to be able to get the bases the same. You know why? Who's the culprit? Like if I do bring this across, I get 3e to the negative x equals negative 2 plus e to the x. Can I get the bases the same? No. You know who's ruining it? The stupid negative 2. I got another term there. If that negative 2 were 0, then I have a factor equals a factor, and that works. But when you have a term, you can't get the bases the same. Stupid negative 2. Stupid negative 2. So what can we do to jumpstart this problem? Anything. Is there anything we can do? F it? Yeah. You mean F the left side? Yeah. I'll tell you this. It's not worth Fing unless it's equal to 0, Brady. Because if it's factored and it's equal to negative 2, we can't set both factors equal to negative 2. Oh, okay. So bring negative 2 across. So we get 3e to the negative x minus e to the x plus 2 equals 0. Okay. Now we can try to F that. Ugh. How are we going to F that? Is there anything that comes to mind that we could do? Okay, if I natural log it like this, I'm going to hamstring myself because now I have the natural log. I'm in your desk. You want to sit here today? Yeah, I've already warmed it up. I'm not going to give it away. I got the natural log of 3 terms. Can I distribute the natural log inside of itself? Is that legal? No, it's not. I can distribute like a natural log of 6, because that's the number, into some parentheses, but I can't distribute a log inside its own argument. So taking the log of both sides kind of messes me up. Bully. I told you were going to like this one. How about this? Is there anything I can do with e to the negative x? I can bring it to the bottom. That's what you mean, right? Let's try that. So that's 3 over e to the x. Yes? 3 times e to the negative x is the same as 3 over e to the positive x. Okay, minus e to the x plus 2. Now, what did we do on example A when we had a denominator? What did we do on the warm-up when I had a fraction? I multiplied both sides by the LCM. Yeah. So simply by rewriting it with a positive exponent, I've created a denominator. Now what I can do is I can do what Wyatt said yesterday. I can kill it, right? So I'm going to multiply both sides by e to the x because that's the LCM. That's the only denominator. It's just giving me something to do. It's algebraically manipulating the equation, just giving it a different look, and then jumpstart something else that I can do. Is it going to bear fruit? Is this going to be the way to work the problem? I have no idea. I've never worked this one, which makes it fun. If I distribute now, the e to the x divides out in the first term, and I'm left with 3. What do I get in the second term? What's e to the x times e to the x? Yeah, it's e to the x quantity squared, like that, right? Which, what would we do with the exponents right here when it's raising a power to a power? We'd multiply them, so that becomes e to the what? 2x. I'm going to write it like that. E to the 2x. Or you could say we're multiplying and the bases are the same. You add the exponents, right? X plus x is 2x. And then I get plus 2e to the x, and that still equals 0. Okay? Nice, baby. Doom, 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 doom. Nice, baby. Hey, let's write this in descending order now. Negative e to the 2x plus 2e to the x plus 3 equals 0. That almost looks like a quadratic trinomial, doesn't it? I have a e to the x quantity squared, which is e to the 2x, and then I have a non-squared variable, and then I have a constant. I also have a negative leading coefficient. Yucky, gross, negative leading coefficient. You know what I'm going to do? I'm going to multiply both sides by -1. You can factor out the negative, but now because it's equal to 0, just multiply both sides by -1. We get e to the 2x minus 2e to the x minus 3, and 0 times -1 is still 0. Now here's what's cool. Watch this. Off to the side here. What if this were actually just x squared minus 2x minus 3 equaling 0? We could factor that, right? We could double bubble that dude. It would be x, and then it would be -3 and plus 1. Yes? Okay, this right here is written in quadratic form. As long as you have a squared quantity for the larger exponent and a non-squared quantity for the smaller exponent, you can write it in quadratic form. So what this is going to factor into is similarly something that double bubbles. It's still going to be a -3 and a plus 1. The only difference is instead of x squared and x, we have e to the 2x and e to the x. So we use the smaller exponent to go in there. It's a factorable quadratic. As long as the larger exponent is twice as big as the smaller exponent. We did this in Algebra 2. We actually did this in Algebra 2 this year, just a couple of weeks ago. So I know you've seen it. It just doesn't show up that often. But it's a factorable quadratic form. Okay, so now that we have it completely factored and it's equal to 0, Now we can set both factor equal to 0. So now we get e to the x minus 3 equals 0, or e to the x plus 1 equals 0. And now we can solve these equations separately. So what I'm going to do here is I'm going to separate the terms. I get e to the x equals 3, and now who comes to the rescue? ln. What's ln of e to the x? X. And what's ln of 3? It's just ln of 3. That's a number, right? That's legal. We can only take logs of positive numbers. Is 3 a positive number? Yep. How about over here? We get e to the x equals negative 1. I take the natural log of both sides, and I get x equals the natural log of negative 1. Is that legal? Ruh-roh. Natural log of a 0 or a negative number? I'm afraid that's DNE. We can only take logs of positive numbers, not 0 or negative. So who's the only solution? Natural log of 3. Okay? There you go. If you see one like that on a test or a quiz or your homework, that's what you're going to do. Just bring the negative exponent to the bottom and then get rid of the fraction by multiplying both sides. Write it in descending order, and it should turn into a factorable quadratic for you. All right. Comments, questions, quips, quotes, concerns. Good, clean jokes? The classic good, clean joke when I was young. Y'all have heard it too, right? Hey, you want to hear a dirty joke? Sure, I want to hear a dirty joke. 2 white horses fell in the mud. Oh, that's dirty. Can you imagine trying to get them clean again? That's actually a clean joke. It's a clean, dirty joke. I don't know why there was always 2 of them, but it was just 2 white horses fell in the mud. And why was it horses? Why wasn't like two white dogs played in the mud? No, the horses weren't even playing in the mud. They actually fell into the mud. Like, I'm falling, right? And then splash. And now they're dirty. Y'all heard that joke before, right? No, that never circulated on the playground in elementary school. Man, I grew up in the Rio Grande Valley. That was going all through the valley back in the day, in the late 70s. Y'all remember the late 70s? Just like yesterday. Oh my gosh, I'm getting older. I'm getting a little blonde in my beard. Hey, let's solve this equation. 500 over 1 plus 25e to the 0.3x equals 200. Is this an exponential equation? Yeah, you can call it one because it has a variable in the exponent. Now, does anybody in here recognize that form on the left-hand side? You do, Brady. What special name did we give to that modified exponential growth that has that physical appearance in equation form? No. No. This was a free response question on one of your tests. I don't know if it was the Worst Fest question or the Wassel Fest question. What's that? Yeah, it had the limit as x went to infinity, right? It's the limit to growth. The COVID, the flu spread through the school, or the titanium bracelets didn't work. They didn't increase balance. What did we call that type of function? Logistic! You got it before I finished. Ryan's on fire today. I said Girls Gone Wild, and he got all excited. That's a logistic equation. Yeah. Remember how we solved logistic equations like this back in the day? I gave you a calculator. You graphed this in y1, you graphed this in y2, and you found the point of intersection, right? No. We don't need the stupid calculator now to give us an approximate answer, right? We had to round approximate answer. We have the skills now to solve it by hand to get an exact answer. Yeah, go us. Okay. What would be the first step? Multiply both sides by what? 1 plus 25 e to the 0.3x. So I'm going to write it like this. 500 equals 200 times the quantity 1 plus 25e to the 0.3x. Okay. Now, I have 2 options here. I only have variables on the right. Bless you. Bless you. I don't have variables on the left. Uh-huh. I can either A, distribute the 200, that's A, or B, I can divide both sides by 200. Divide by 200? Okay. So if I divide both sides by 200, I get 500 divided by 200 equals 1 plus 25 e to the 0.3x. Yes, yes? Say what? Just 5 halves. Very good. The decimals, the zeros divide out, and I'm left with 5 halves equal 1 plus 25 e to the 0.3x. Now, I have another option here. I'm at another fork in the road. I can either keep working with 5 halves, I can call it 2.5, which is a decimal. Ugh. We don't really work with decimals in here unless we have a calculator. Or I can get rid of the fraction again by multiplying both sides by 2. I'm going to kill it. I'm going to multiply both sides by 2, and I'm going to distribute the 2 to the right-hand side, which gives me 2 plus 50 e to the 0.3x. Now, you could have gone straight from here to here if you realize, hey, 5 halves is not going to simplify down to a nice integer, but I could divide both sides by 100, right? I could get rid of the double zeros on both sides, and then instead of distributing a 200, I'm only distributing a 2. Or you can do it in sequential steps like we did. There's really no wrong way to eat a Reese's peanut butter cup. And that's what we're doing here, right? Or skinning a cat. What if you get hungry while you're skinning a cat and you eat a Reese's peanut butter cup? You can do it differently every single time and you'd still be correct. All right, now here's our goal. We want to get at the x. We got to start peeling back the layers. What's the first thing standing in our way on the right-hand side? Nope. The 2. I got to isolate the variable term first. So I got to subtract 2 from both sides. 5 minus 2 is 3. So I get 3 equals 50 e to the 0.3x. Once you isolate the variable term, now you got to isolate the variable factor. The factor is e to the 0.3x. So how do I get rid of the unwanted 50? Divide. So I'm going to get 3/50ths, which is a fraction. That's okay. Equals e to the 0.3x. Now I have e by itself. I'm not going to get the bases the same. So who comes to the rescue? Natural log. So I'm going to flip sides here too. The natural log of e to the 0.3x is just 0.3x, and I'm left with the natural log of 3/50ths. Now, 0.3 is a decimal. We don't have any decimals in here yet. So here's what I'm going to do. What is another way to write 0.3 as a rational number? 3/10. So I'm going to write this as 3/10 x equals the natural log of 3/50ths. I do not like having expressions that are part decimal and part fraction. They need to be either all decimal or all fraction. It's kind of like a mixed language, Spanglish. Now to solve for x, I just multiply both sides by the what of 3/10? Reciprocal, and I get x equals 10/3 natural log of 3/50ths. And there's your final answer. That's your exact answer. Now, can we play with that? Yeah, we could call that 10/3 times the natural log of 3 minus the natural log of 50, if you want. And then if you want, you can even distribute the 10/3 to each of them. 10/3 natural log of 3 minus 10/3 natural log of 50. And now if you want, you could bring the 10/3 up top, or watch this. You could just bring the 1/3 up top and say it's 10 natural log of the cube root of 3 minus 10 times the natural log of the cube root of 50. If I just bring the 1/3 up, then the arguments become cube roots. And now I can factor out the 10, or I can bring the 10 up if I want. That's probably good, right? Yeah. So which one of those answers is correct? All of them. They're all correct. Yeah. I like the original one that we got, to tell you the truth, or the second one where we get rid of the fraction, 3 minus 50. Either one of those are good to me. I don't know if I'd bring the 1/3 up and call it the cube root. The whole purpose of logs is to make things simpler looking and smaller numbers, not bigger numbers. So 10/3 natural log of 3/50. That is the exact answer. We don't need the calculator anymore to find the point of intersection. We're advancing in our skill set. We're growing as human beings. How does that feel? Feels pretty good. You're a better person now than when you woke up this morning. That's for sure. Right? Students gone wild. With logs, right? Featuring logarithms. Yeah. Logistic equations. Okay. We have enough time to introduce log equations. Now, we've already seen log equations when we studied logs. We had simple log equations such as this, right? Do you remember how to solve a simple log equation such as this? You could do the around the world thing, right? Which would mean stupid highlighter, means 3 to the fourth equals x plus 2, right? That's doing the around the world thing. Or you could exponentiate both sides like that, right? Either way. And then 3 to the log base 3 of blob is the blob. Either way. And then, of course, we get x plus 2 equals what is 3 to the fourth? 81. Very good. And then all we got to do is subtract 2 from both sides, and we get x equals 79. Yeah. So those were simple log equations. We've already solved log equations like that. Now, there is something we want to be very, very considerate of. Because it's a log equation, is the domain of logs all real numbers? Nope. No. The domain of logs is restricted. Okay? We can only take logs of what types of numbers? Positive. So do you remember how to find the domain of a log function algebraically? You take the argument and you say it's strictly greater than 0. So for us, x plus 2 has to be greater than 0, which means x has to be greater than negative 2. We got an answer of 79. Is 79 greater than negative 2? A little bit. So does it work? Yeah. Now you can either do it that way, or you can try out your answer. Plug it in. What's 79 plus 2? 81. Is 81 positive? Yeah. So there's two ways to try out your answers, but we have to be a little bit more careful with log equations because they have domain restrictions. Okay. So that's what we're going to do. We're going to find the domain of the equation prior to solving the equation. We're going to solve it after we find the domain. Now, example 5 says to solve this in two different ways, by converting it to exponential and exponentiating both sides. I think I already did that, right? It works the same way. Around the world gets you 3 to the 4 to the x plus 2. Exponentiating both sides gets you that. So we've already done this one. We did it. It's right up here. So we're going to start tomorrow with example 6. Okie dokie? And that should be it for today. We got finished with exponential equations. We are now well on our way to logarithm equations.